guys, today we start Unit 9, Exponential Functions. Beginning of the year we did linear functions, then we just did a whole bunch of stuff on quadratic functions, and now we're going to do a very short unit on exponential functions. We looked at exponential functions just a little bit at the beginning of the year when we compared linear with the equation, linear, quadratic, and exponential functions, how their equations differentiated, how their graphs differentiated, and how, like, if you read it in a chart, how that differentiated. So we'll revisit that a little bit today. Now, I wanted to show you my best example that someone shared once about exponential functions, something that will help you to understand. This is the picture here is an exponential function that's been graphed in regards to radiation after Chernobyl. So the idea that when Chernobyl happened, and I'm not a very big science person, don't know a lot about it, but there's a whole lot of radiation, enough to kill a lot of people and a lot of things. And if it didn't kill you right away, it could kill you over time. And so they've evacuated that area. And as the years pass by, that radiation level goes down, and it'll go down, and it'll go down, and it'll go down. But a million years from now, it will never be completely gone. It will never reach zero. So that's what you're going to see with these exponential functions as they come down. As you can see with these graphs right here, it looks like they're going to touch the x-axis, which is where y is 0, but it will never actually touch it. So let's get going. That's my best example for introducing exponential functions. Here at the top of your notes, you can see what a linear function looks like. Where x is to the power of 1, quadratic x is to the power of 2, and exponential functions, the x is the exponent. So they're really easy to identify. Exponential functions, I'm just reading right off here. You can see the formula right here. And very important to note that where the a is, this is the y-intercept. Thus, y equals b of x, a is 1. In other words, this is the parent function, y equals b of x, and you don't see the a because a is 1. That is also telling you where it is crossing over the y-intercept, which is at 1. If you don't know what I'm talking about yet, don't worry about it. Okay, where b is the base, this is the constant. It's going to be a constant value that's changing by, and then x, as you can see, is the variable. So if a is greater than 0 and b is greater than 1, actually, if you take a look at exponential growth and decay, a is always going to be greater than 0. But when b is greater than 1, then it's going to be showing growth. It's going to go up like that. But if b is less than 1 but greater than 0, like a half, a fourth, 2/3, then it's going to be the exponential is going to go, the growth is going to go down. We call that decay. So for both of them, the domain, again, seeing as we won't necessarily put restraints on anything, the domain is all real numbers. And the range is going to be, y is always going to be greater than 0. Now notice I didn't say it's going to be equal to it. It's always going to be greater than 0, but it'll never actually be 0. For decay, it's the same thing. The domain is all real numbers, and the range, y is greater than 0. Now, exponential functions, just like quadratics, just like linear, we can do transformations with them, and then these things might change, but your basic exponential function, this is true. In fact, that line, that x-axis, that place where y is 0, we call that the asymptote. A-S-Y-M-P. I'm having to look at my cheat notes because I surely do not want to misspell that. And so it's a horizontal asymptote. It is a horizontal, the x-axis is a horizontal line that the graph will never touch. Okay, so here again we have that parent function, and it says because anything raised to the 0 power is 1. The parent function will cross the y-axis at 0, 1, because anything raised to the 0 power is 1. So the y-intercept will be 1. Again, you'll see how all this is played out. So we have an example here, and I've already put it into the calculator so we can already see answers. I don't want to spend the time doing that together. Plus, I can't do the calculator on this format. And so, but I fill out the chart. It was 3 to the power of x, and then we gave the exponent values starting with a number -2 and going all the way to 2. And you can see what y becomes. If I graph these points, then you're going to, if you notice, b, this number right here, is more than 1. So would that be growth or decay? It's going to be growth. And so I'm not going to be perfect, but you can see it's going to come up. It's going to cross right there at 1. That's right where it's going to cross. And then it's going to go up, and the more farther over, then it just kind of starts to shoot up. It'll start going up really fast. So that's basically what it looks like. We got a little off the graph. Go ahead and erase that. All right, so that's what you're looking at. Again, the y-intercept is 1 or 0, 1. X is all real numbers. The asymptote y equals 0, and the range is y is greater than 0. It can be that easy. Let's go to the next one. So here you can see that b is less than 1 but greater than 0. I went ahead and filled it out. Of course, you would put these 1/3 to the power of -2. You could put it into a calculator or work it out yourself. So 1/3 is b is less than 1 but greater than 0. So will this be a growth or will this be a decay? That's correct. It will be a decay. And so it's going to, guess where it's going to cross the y-intercept? 1. So I'm going to go ahead and put a dot there, kind of a target here, because I don't want to take the time to do all the points. Oh, my artwork is horrible. But you get the idea. You can kind of see how it's just going to go on down. It's going to it's going to cross over at 1. It's going to get really close to the x-axis, but it's never actually going to cross it. So here again, the y-intercept is 1, or we could say 0, 1. The domain is all real numbers, asymptote, and then the range y is greater than 0. All right, see some consistency there. Let's move on. Now, so we looked at charts, graphs. Now, how about if you already have a chart? How can you tell if it is exponential? So you can tell if it is exponential if, let's see, do the domain values increase or decrease in constant intervals? What about the range? Is it a constant interval or is it a constant factor? If it's a constant factor, then it's going to be, yes, it's going to be quadratic. If it was a constant interval, it'd be linear. So let's look at this first example. I can see that this is going up by 5, constant. But if I look down below, -32, -30, that doesn't work. But there's a constant factor of 1/2. So if that's what I see, then yes, it is exponential. It was pretty quick to look at and see. And we did a little bit at the beginning of the year also. Let's look at the next one. This one's going up by 3s. And then here, it looks like it's going down by 4s. So this would be a no. This one would be linear. Okay, let's look at a word problem. So as you can see, we have an exponential function here that models the amount of soda consumed in the world. I don't know how accurate this is, but it says where C is the amount consumed in billions of liters and T is the number of years since 2000. Okay, so what do we know just looking at it? What's the y-intercept of the equation? Now, do you remember the original equation? Y equals ab to the power of x. This is the y-intercept. So what we've been doing when we graphed it, y was always 1. So this, it is 179. So what is the y-intercept? 179. So what does that tell us? That tells us that the domain, what do you think the domain's going to be? All real numbers. And the range, what do you think the range is going to be? Same thing, y is greater than 0. So 179 is the starting point. And then it wants to know over time, over, let's see, 2005, which is t would be 5 at that point. 2010, t would be 10 at that point because it's years since 2000. So we're going to take the formula that they already gave us. We want to know what C is, how much is consumed. In the beginning, it was 179 billion liters. So over a, let's see, a 5-year period, I'm going to go ahead and we're going to pretend we all put that into the calculator. C becomes 206.5 billion liters. All right, and then we're going to do it again. We're going to do it at 10 years. 179 times 1.029 to the power of 10. Put that in your calculator and you get 238.2 billion. What's a point right there? Liters. So you can see the equations are pretty easy as long as you remember what the A and the B and the X are. Good luck. Hopefully this is under 15 minutes and I'll see you later. Bye-bye.